Welcome to Chapter 17, Section 2. We're talking about capacitance today, and we're only doing the conceptual parts with these equations. We're not going to cover anything with permittivity. So if you have more questions about that in class, we can talk about it then. So what we're going to do in this section is we're just going to relate capacitance. We're going to learn what that means to this idea of storing electrical potential energy in the form of separated charges. So in order to understand what capacitance is, we need to know what a capacitor is. So a capacitor is just a device that stores electrical potential energy. So that energy is stored in the form of electrically separated charges, okay? So what happens in a capacitor is you have these two plates, okay? And to begin with, like in this picture here, the charges on each are equal and opposite, okay? And then what you do is you connect it to a battery. Okay, and once you close the circuit, then the charges are going to start moving. Okay, so the negative charges will come towards the battery, and then the battery will give negative charges to the plate. Okay, and so what happens is you end up with an overall positive charge on one side of the plate and an overall negative charge on the other side of the plate. So now you have this electric field, right? And that electric field you can use to store energy because we know these charges want to jump across to the other side of the plate. So we're storing that energy by keeping the charges on one side and not the other. So when we measure capacitance, okay, it is measured as the ratio of the magnitude of charge on a plate to the potential difference. So we write that out as C equals Q divided by delta V, our potential. Okay, and the unit for capacitance is the farad. Okay, and the amount of charge typically stored is so small that most of the time the range for capacitance is only microfarads to picofarads. So if you remember, micro means 10 to the negative sixth, and pico is really small. Pico is 10 to the negative 12. Okay, so that's how we measure capacitance, is using this unit. So let's take a closer look at everything that's going on. So we have this picture here, and this is to help us understand the equation for capacitance. So we have C equals Q divided by delta V, which is our potential difference. Okay, and so what happens is we end up with all these charges accumulated on one side, and so the other side is positively charged, okay? And so the charge on each plate is Q, okay? And we've got the distance that occurs between the plates, and we've got the electric field generated by their separation. So if you remember, our potential difference can be calculated by using the equation negative ED. So it's the electric field times this distance. Okay, so this is allowing it to store charges, because later if we connect it to a circuit, right, so imagine I'm closing the circuit here, right, suddenly all of these negative charges are going to move around. Okay, so they have the potential there to do. So some of the things that we can do to change how much capacitance a capacitor has, okay, is we can change the type. The examples I've been giving you here are what's this one called a parallel plate capacitor, okay, where it's just two flat plates. You can also have ones, for example, like this, where you've got a rod inside and a cylinder outside, okay, and one of them is positive and the other is negative, and so this is a cylindrical capacitor. So the type of capacitor controls how much capacitance it has, and in both of these examples, case size controls how much capacitance something has. So the more area there is for charge to accumulate, like the bigger area here or the bigger area here, okay, it will give you more capacitance because you can increase the charge held on the plate. The other thing that we can do to affect the capacitance is change the material between the plates. So most of the time they don't put empty space between the plates, they put something called a dielectric, okay? So dielectric can be used, and this increases the charge a plate can hold by reducing the electric field between the plates. So less electric field means less force to move the charges from one side of a plate to another. So let's look at what that means in a picture. So here, this is an example of a capacitor that has a dielectric in it. So this orange color is the dielectric, and it has molecules that can be polarized, right? And so what it does is it reduces our electric field. Okay, and in reducing the electric field, remember our equation is Q divided by delta V. That makes our potential difference smaller, which also increases our capacitance. And also, then our Q's can get bigger without breaking the capacitor. So overall, this kind of situation will increase your capacitance by decreasing the electric field. Now, if you don't do this, okay, or even if you do this, you can still get too much charge on one of these plates. And if there's too much charge, then the electrons are going to force themselves across the plate and break it, essentially. Because as soon as an electron goes across here, then it can no longer sustain an electric field. So if that happens, you get this cool pattern. You can imagine that this is a capacitor, okay, with one side here and one side here. This is a picture from your book. Okay. And what happens is if there gets to be too much charge on this side of the plate, the electrons in the field get strong enough so that the electrons can jump across. Okay, and it kind of creates this cool pattern that looks like lightning. And we'll learn a little bit later that really this is very similar to how lightning does indeed work. It has to do with charges getting stored up. So capacitors will stay charged until you discharge them, okay? And so to discharge them, you just need to connect them to an electric circuit or other conductors, okay? So if this is our capacitor, and you'll start to see this symbol a lot. This is our symbol for a capacitor as we start learning about electric circuits here shortly, okay? And all you have to do is you need to take that and connect it to some other circuit, okay? And once you do that, then all the charges that had stored up will flow back around until the charge is 0 again on each plate. So that's what happens when you discharge it. So that's how it does work. Okay. So capacitors store this electrical potential energy. Okay, and we can calculate the amount of electric potential energy they stored using this equation, where it's 1/2 the charge times the potential difference. And that takes us back to talking about work, potential energy, and capacitors. So we had the one picture where we connect the capacitor to a battery, okay? And you're going to learn about these symbols later, but this is a battery, okay? And what happens is it forces the electrons together, so you end up with a negative charge here and a positive charge here, okay? So they're sitting there, and there's this electric field, and it's waiting to move, right? And then what happens is instead, we're going to connect it to something else, okay? So we put in a circuit here, and this just represents that there's something else going on. And it allows all these negative charges to move around the circle to get to the positive charges and balance out until Q is 0. So this is storing energy, right, in the form of that potential energy to do work by moving the charges. Okay, so a capacitor really just stores potential energy. Okay, that's really the key, and it does that so it can do work. That's the whole reason we talk about potential energy, so we can see how that potential energy is converted into a more useful energy, like kinetic energy, or in this case, work. Okay, so that's really the key to this. Okay, so I just wanted to briefly talk about what capacitors have to do with your daily life, because there's a really modern application that we see every day that uses capacitance, okay, and that is your touch screens on your phone. So touch screens are a relatively new technology, and they use capacitance to do that. So some of the best screens are called touch capacitance technology, okay, and you can find a complete explanation at this web address, but I'm just going to do a short little one for you. When you use your touch screen, you are using this idea of capacitance, okay? So touch screens, and in this case the example is the iPhone, is that it just has a whole bunch of different layers between the picture that you actually see and where you're touching, okay? So they've got a protective cover and then some bonding material, but here what we care about is these circuit lines, okay? So these are lines that conduct electricity, okay? And they're set this way and this way because that helps identify where your finger is on the screen. Okay, so let's look at how these two sets of lines now use capacitance. So what happens, okay, is if you imagine these is one of the lines, is these are one of the others, okay, they're creating an electric field that goes out past the plastic or glass where you're touching it. So what happens then is when you touch your finger, you change the direction of the field lines, and some of them now can reach the other line, okay? So when that happens, then you're going to get electricity that is conducted, and you're changing that electric field. So charges move. And based on where your finger is and which lines are conducting electricity, okay, the computer can determine what it is that you're touching. So every time you use your touch screen, you are using capacitance. Okay, and this idea that we've talked about changing electric fields and storing charges. So I will see you guys in class. Go ahead and let me know if you have any questions there, and I hope you enjoyed.